Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IZZAT bin JAMIRUDDIN and my metric number is DD24402. So I will present the introduction of our group project, which is I will tell about the background and problem description. So in engineering, analyzing fluid flow is very important to ensure that system design are safe, efficient and optimized. And then why real flow is difficult? So real fluid flow is usually complex because it involves effects such as viscosity, turbulence and compressibility, which make the analysis more challenging. So to simplify the analysis, this project uses potential flow theory where the fluid is assumed to be incompressible, inviscid and irrotational, which is these three reasons that the problem involved in this project. Okay, so under this assumption, the fluid flow can be described using the velocity potential function that satisfies Laplace equation, which is a key equation studied in the different equation subject. And then, although potential flow is an idealized model, it provides useful insight into flow pattern, velocity distribution, and pressure variation, and is commonly used as a preliminary analysis tool in engineering design and evaluation. Therefore, the project of this study is to model the fluid flow system using potential flow theory, apply Laplace equation, and analyze the resulting flow characteristic.
For this study, the fluid flow is modeled using potential flow theory. The independent variables are the spatial coordinates x and y, while the dependent variables is the velocity potential. So the velocity components are obtained as the spatial derivatives of the velocity potential. So simplify the governing equations. Several assumptions are made. The flow is incompressible, inviscid, irrotational, and steady. Under these assumptions, the governing equations reduces the Laplace equations, which is elliptic partial differential equation. This equation forms a mathematical foundation for approximating the fluid flow in this study.
Assalamualaikum warahmatullah. My name is Muhammad ZAIM bin RAMZAN. My matrix number is CD230070. And so for now, I will talk about the boundary and initial conditions. As I can see, this is all of the key point of the boundary and initial conditions. So the boundary and initial condition are required to obtain a unique solution to Laplace equation and to represent the physical constraint of the fluid flow system. At the solid wall, a non-penetration condition is applied, meaning fluid cannot pass through the wall. At the inlet, a uniform flow is prescribed using the velocity potential. Since the flow is assumed to be steady, initial conditions are not required. So for the next one is about the solution methodology. For the next one is solution method. So the key point is about the governing equation Laplace equations. Is solved using analytical or numerical methods. Also, it's a chosen method that is a separation of variable. It's suitable for simple geometry and linear boundary conditions. So the fluid flow in this study is governed by Laplace equation. This equation can be solved using either analytical or numerical methods. So in this project, the method of separation of variables is chosen because the geometry and boundary conditions are simple. This method provides a clear and efficient analytical solution for ideal potential flow. That's all it for me. Thank you so much.
Assalamualaikum, my name is Muhammad AZZIM bin Muhammad NAJIB. My number matrix is DD230018. My part is solution and sample calculation. First, on the left side, it shows the general solution for the velocity potential obtained using the method of separation of variable. The general form of velocity potential is Vxy equal A cos lambda x plus B sin lambda x CE power of lambda y plus DE power of negative lambda y. This is the general solution of Laplace equation for two-dimensional flow. Next, based on the given condition, we consider a uniform flow where the velocity potential is simplified to Vxy equal uy. This represents a flow moving uniformly in the vertical direction. In the middle part, we verify this velocity potential using Laplace equation. We calculate the second derivation of v with respect of x and y. Both second derivation are zero, so when it substitute into Laplace equation, the result becomes zero. This confirms that the chosen velocity potential satisfies the Laplace equation. On the right side, it shows case 1 where the inlet velocity is u equal 1 ms. Using the velocity potential, we calculate the velocity component. The horizontal velocity u is 0 and the vertical velocity v is equal 1 ms. The velocity magnitude is therefore 1 ms. This result shows that the flow is uniform, steady, incompressible, and irrotational, which is consistent with the assumption of potential flow theory. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to Dr. Hamidun and all my friends. My name is Muhammad SHAHRUL bin AHMAD, and today I'll be sharing our result and discussion for our projects. So, our project focuses on the numerical analysis of fluid through a two-dimensional duct. We are using the Laplace equation, which is a second-order partial differential equation, to model what we call a potential flow. So, the core of our modeling is to assume the fluid is ideal, which is meaning it is incompressible, irrotational, and also inviscid. So basically, we are looking at a steady state flow where there is no resistance to motion and no energy loss due to friction. So to solve this, we implemented the infinite difference method in Feynman, which allow us to iteratively calculate the velocity potential across the entire channel domain. So here, we also include our result for two graphs, which is for the first one, we are using the 1 meter per second, and the second one is using 2 meter per second. So to understand the behavior of the system, we conduct a parametric study focusing on two key variables, which is first one is inlet velocity and channel geometry. So first, we vary the inlet velocity, which is known as u. We found that an increase in velocity leads to a proportional increase in the magnitude of the velocity field. So, however, the overall streamline pattern remains unchanged, confirming the linear nature of the Laplace equation. Next, we look at the channel height, which is known as h. So, our results show that a larger channel height allows the streamlines to spread over a wider area, while a smaller height confines them. So, crucially, since we neglect viscous effect, the fluid does not accelerate or decelerate purely based on these cross-sectional challenges. As you can see in our first figure, our streamlines are straight and parallel, validating that our model satisfies the boundary condition for the stable and uniform flow. So for the summary, in the conclusion, our study confirms that based on our results, so the potential flow theory is an excellent tool for preliminary engineering analysis because it provides clear and predictable results for general flow patterns. However, we must acknowledge the inherent limitation of this idealized model because it ignores viscosity. It cannot capture wall shear stress, boundary layer formation, or any energy losses due to friction. It also cannot predict complex phenomena like flow separation or turbulence. So therefore, while the Laplace equation is perfect for early stages, design or decision, and understanding fundamental flow structures, it is more advanced model, such as those based on the Navier-Stokes equations. So it will be necessary for a detailed representation of free fluid behavior in a practical engineering applications. So that's all for me. Next, I will pass to my friend for the conclusion. Thank you.
So I will continue to jump into the conclusion, which is in conclusion, this project demonstrates how differential equation concepts are applied to approximate fluid flow using potential flow theory and Laplace equation. And then by modeling the fluid as an ideal flow and applying suitable boundary conditions, the flow characteristic was successfully represented in a simplified mathematical form. And then from an engineering perspective, this simplified approach helps us understand basic fluid pattern and system behavior, and it is especially useful during the early stages of engineering design. So in our group project also can link to the real practice, which is the analysis is theoretical. Even though the analysis is theoretical, it provides a strong foundation before moving on to more advanced methods such as numerical simulation and computational fluid flow dynamic or CFD. For the future improvement, the analysis can be extended by including more realistic flow conditions such as viscosity and more complex geometries, such well as using computational tools to compare theoretical and practical results. So overall, this project strengthened our understanding of how differential equations are connected to real engineering application, particularly in modeling and analyzing fluid flow system.